Hello and welcome to this session. So in this session we're going to be talking about routing protocols, and routing protocols are the standards that help us to communicate from one router to the other in case we have not assigned a next hop address of a path to a network that a user wants to get to in a specific network. So this helps us to communicate from one router to another dynamically without statically configuring the next hop address. So even to this kind of content, remember to hit the like button, comment down below, and also subscribe to my channel so that you're updated each time I upload a new video. So let's get into routing protocols. Now, in my previous video, which is the IP routing video, I talked about the different kind of routes that we can find in our routers. We can have a static route, which is administratively added. That is, the system administrator configures the next hop address of a destination network to a router. And this is very believable because you're going to, you specifically know the IP address of what router you want to go to, the next router that you want to go to. So you statically you as the system administrator will statically assign that specific address, and that route will be a static route. We have what you call as the default route, and this is done to help reduce the routing table maintenance. And a default route just means that if you receive traffic from a user inside your network and you don't know where this traffic is supposed to go to, so you're going to use any available next hop router that is closest to that destination network that you want to route to. So it's an any-to-any connection. Any router can connect. Any router that knows that path to that specific destination network that you want to get to will respond to you, and that will create a default route. Now, we have what you call as a dynamic route, and these routes are determined by routing protocols, and these are basically deployed for network scalability. And what I mean by network scalability is that you want to deploy more routers in your network, and you don't want to specifically go to each router and configure the static IP addresses of the next hop address or the next hop router that is supposed to guide you to the destination network. So that is where dynamic routing or the routing protocols come in. Now, we have a few terms to note when it comes to routing protocols. We have to understand what we mean by administrative distance, which is denoted by AD, and this is basically the believability of a route. We have just said that a static route is very believable, and by default a static route will have an administrative distance of 1, and the lower the better. Now, we have what we call as the distance vector, and the distance vector considers what we call as a hop count. Okay, and this is a distance vector routing protocol. When I'm talking about distance vector, we have what we call as a link state routing protocol, and this uses the Dijkstra algorithm to maintain a database that is a map of the network topology. So each router will have a map of a topology of the topology of the network, or how routers are basically interconnected with each other. We have what we call as the path vector routing protocols, and this considers a path attributes. This could be the number of hops, and it could gives you different routes to that specific direction. So it's going to depend on the path that you're going to take, and what condition is that path in. So some call them the hybrid vector routing protocols, or the hybrid routing protocols, but they are actually path vector, because okay, let's get into interior gateway protocol. And an interior gateway protocol is the protocol that runs within an autonomous system, such as a company or an ISP. This could be routing protocols such as OSPF, RIP, and ERGIP, which you're going to get into later in the video. We have what we call as an exterior gateway protocol, and this helps us to run between autonomous systems. It runs between autonomous systems and helps us to communicate between those two different autonomous systems. And when I'm talking about an autonomous system, I'm talking about a system or a network under one administrative control. Okay, so that is what I mean by autonomous system. And these are some of the terms that you're supposed to understand when it comes to routing protocols. We have talked about interior gateway protocols and exterior gateway protocols. The difference between the two is internal communication and external communication. For interior, they help us to communicate with inside the networks, inside our networks. So we deploy different routers in our networks, and we are able to communicate through interior gateway protocols in between the routers that we have in our internal networks. For external networks or networks that are outside our administrative control, we use what we call as exterior gateway protocols. Now, for interior gateway protocols, we have two types. We have distance vector and link state, and we stated the difference between the two, such that distance vector is considers the path cost, or what the number of hops that you're going to go through before you get to your destination, or the number of routers that you're going to go through before you get to your destination. We also have what we call as a link state routing protocols, and these are routing protocols that allow us or allow routers to keep a database of how the network looks like. It keeps a database of the network topology. In the exterior gateway protocols, we have what we call as path vector, and we just said that the path vector considers the path attributes. What condition is that path in? And we could also have multiple paths to that network or to the destination network. For distance vector, we have RIP version 2 and version 1. We have ERGIP, that is for IP version 4, and in a link state for IP version 4, we have OSPF and ISIS, which is a intermediate system to intermediate system. And for IP version 6, for the interior gateway protocols, specifically for the distance vector protocols, we have RIPNG, and ERGIP IP version 6. For link states in the interior gateway protocols, we have OSPF version 3, and ISIS, that is intermediate system to intermediate system, IP version 6. For the path vector exterior gateway protocols, we have BGP4 for IP version 4 and BGP MP for IP version 6. We're basically going to go through the common ones, that is RIP, OSPF, and BGP. ERGP and ISIS will depend on the networking vendor that you have, or the network devices that you have bought will vary according to the network vendor that you purchased your networking items from, or your routers from. Now, each routing protocol has a different administrative distance, and we talked about administrative distance as the deliverability of a route to a router. And these different routes or protocols have different administrative distance. For a directly connected route, the administrative distance is 0. If a router is connected to another router, if a router is directly connected to another router, then the administrative distance is 0, meaning that that route is very believable. If you configure the next hop address, that is a static route, it will have an administrative distance of 1. For EIGRP, the administrative distance is 90. For OSPF, that is open shortest path first, the administrative distance is 110. For ISIS, the administrative distance is 115. For RIP, the administrative distance is 120. So let's get into the considerations that we make when we are choosing a routing protocol. What do we want to consider when we are choosing these routing protocols, or whatever we want to use in our network? We're going to consider scalability. Remember, RIP, which is a routing protocol, only has a maximum hop count of 15. So if you have 16 routers, then 16 will be infinite. That router will be unreachable in your network. So RIP is not scalable. We have what we call as vendor interoperability. That is, if your network does not contain gadgets or devices from one networking vendor, then you're going to basically choose a routing protocol that is going to fit your network, because you are not specifically relying on one networking vendor in your network. We also have what we call as a familiarity with the routing protocol. That is, your team members have to be aware of whatever you're using as your routing protocol in your network. Your fellow system administrators must know that we're using EIGRP, and they must be familiar with the EIGRP or whatever routing protocol that you're going to choose to use in your network. We have what we call as a convergence in case of failure of one router, and this is the time that it takes to recover for your network to be up. Okay, so that you can get failover services. And what I mean by failover services, we have different protocols. We have VRRP, we have that is the hot standby routing protocols, that is VRRP. We have GLBP, that is the gateway load balancing protocol. For VRRP, that is the virtual router routing protocol, and this will vary from one networking vendor to another. If you go to Huawei, you'll hear of the VGMP, that is the virtual group management protocol, and this basically helps us to provide failover services or convergence in case of a failure from one router, to make sure that the user gets to the destination network. Now, talking about routing protocols, we are going to go through 3 of them. That is the RIP, OSPF, and BGP. The rest, I promise to make videos about them, but stick with me as we learn these 3, since RIP was the first to be developed, and it is not scalable, so we use OSPF commonly, and BGP we use it for external communication, or communication with the networks outside our internal networks. So let us look at RIP first. And RIP means routing information protocol, and it's not desirable. It's a distance vector routing protocol, meaning that it considers the hop count, or the number of routers that you have to go through so that you reach to your destination network. And as we said earlier, it's not scalable, since it only routes to a maximum of 15 hops, that is 15 routers. And what routing information protocol uses is the split horizon packet and the poison reverse packet. Now, the split horizon packet prevents a router from sending an advertisement out the interface on which it was received, Well, Poison River sends an advertisement with an infinite metric for an unreachable route. So split horizon will prevent backward forwarding of traffic. That means that if traffic was received on a certain interface, then it will not go back through that interface. And Poison Reverse is supposed to tell you whenever there is failure of a router in between the user and the destination network. So it will just, instead of looping around and advertising those networks to its or advertising those routers in a loop, then Poison Reverse is going to be used to send an advertisement to say that I cannot reach that router, so kindly stop the traffic. Now, for RIP we have 3 versions. We have RIP version 1, and RIP version 1 works with the broadcast packets, is whereby it's sending to each and every host in the network. It does not support VLSM, that is variable length subnet mask. I forgot to say that the broadcast is sent every 30 seconds to just notify that it's there, it's available, and it's only available in IP version 4. We have what you call as a RIP version 2, and RIP version 2 or RIP version 2 uses what you call as a multicast packet. And remember, when you're talking about IP addressing, we talked about multicast packets, and multicast packets are sent to one destination or to one address to which there is a group of routers or devices that have agreed to join that group in order to receive certain updates or information that they require to get from that network. Okay, so they basically join a group, and from this group, when a packet is sent to this specific IP address, and for IP version 4 it's 224.0.0.9, when an IP or a packet is sent to that IP address, then the packet is going to be retransmitted to routers or devices that have joined that or have chosen to join that specific multicast group. Now, for RIP version 2, there is a variable length subnet mask support, and we also support authentication. Now, for the 2 RIP versions that we have looked at, they only support IP version 4. Now, RIP NG, and NG stands for next generation, supports IP version 6, and it also uses a multicast address or a multicast group to get updates from routers. So routers will join this multicast group, and they will send information through the multicast group, whether it's the messages that the hello messages that or advertisements that they are available, they will send to this specific multicast group. Now, let us look at OSPF. OSPF stands for Open Shortest Path First. It is an open standard routing protocol, and it is link state, meaning that every hop or every router has a map of the network. What OSPF does is that it establishes adjacencies with the other routers, and we're going to define adjacencies later in the video. And what I basically mean by adjacencies is that I know about, or I have information about the next router that I'm supposed to go to. I have that information in my database. So if I want to go to a certain network, I'll just refer to my database and forward traffic through the best route, or the open shortest path first. So OSPF works by sending a LSA, which is information, that is the link state advertisement, that is used to construct an LSD, which is a link state database from the received LSAs. So I believe I have made myself clear. So OSPF runs on the Dijkstra algorithm, And the Dijkstra algorithm also runs GPS. It helps. So Dijkstra algorithm, or a Dijkstra shortest path fast algorithm. Believe me, it's very hard to pronounce that. So Dijkstra shortest path fast algorithm also runs a GPS, and how Dijkstra runs is by determining the open shortest path fast. So suppose you have a destination, and to this destination you have multiple routes to which you can use to get to the destination. But when you are traveling, or when you have network traffic in that specific route, there is failure in one route, so you have to redirect to the next open shortest path first. So Dijkstra algorithm helps to run a OSPF, and it attempts to inject the best path for each network into a router's IP. So the state of the route could be in failure, it could be unavailable, or it could be having a lot of traffic, so you need to be redirected. So the factors could be different, but what OSPF does basically is to redirect you to the next open shortest path first. Now you have to note that when you're using a OSPF or any other protocol for that matter, if another protocol is used in the same system or in the same network, then the routing protocol with the lowest administrative distance, or with the lower administrative distance, is going to be used, since it's going to be most believable. Remember that we talked about administrative distance, and the administrative distance is the believability of a route. So if you use two protocols and one has an administrative distance which is higher or lower than the other, then the lower one, the one with the lower administrative distance, is going to be used to transport traffic in that specific network. There's some OSPF terminology that you need to understand. It's what we call as the hello message, and this is a protocol that is used to discover OSPF neighbors and confirm reachability to those neighbors. It is also used in the selection of a designated router. We are going to talk about designated routers later in the video, so stay tuned for that. We also have what we call as the LSA, and this is not a perfect packet, rather it's a information that a router sends and receives about network reachability. So it's not a packet, it's just information. And what we use to carry these LSAs is an LSU, which is a link state update, and this is a packet that carries the LSAs. Okay, and this we have said that LSA is information that a router sends or receives about a network reachability. Now we have what we call as the LSR, which is the link state request, and this is used by a router to request a specific LSA or information about reachability of a network from a neighbor router or a neighboring router. Okay, we also have what we call as the LSAC, or the link state acknowledgement, and this is used by a router to confirm it has received a link state update. So after receiving a link state update, it's going to send a link state acknowledgement to confirm that it has received the update successfully. Now let us talk about neighbors and adjacencies. So neighbors are routers that reside on the same network. Take for example, in your estate you have neighbors, you reside on the same area, and you can greet each other frequently, and these are hello messages when we talk about networking. And neighbors in routers exchange hello messages to the multicast address of 224.0.0.5. okay, so neighbors will send hello messages saying that I'm in this area, so keep information about that. So in IP version 4, the multicast address is 224.0.0.5. In IP version 6, we have the multicast address being FF02:5. So that is the multicast address IP address when it comes to OSPF neighbors. When you talk about adjacencies, we were talking about your estate. You have neighbors, and you have those specific neighbors that know how or have more information about you. Apart from greeting each other, they have some more information about you. So in networking or in routing, we call those adjacent neighbors or adjacencies. And the adjacent routers are neighbors have exchanged LSUs, which carry the information about reachability of a network, and have exchanged database description packets that they have given how the state of their database. They have exchanged the state of their database with each other. So if one router needs to confirm the route to another path, then it's going to consult its adjacent neighbor, and it's going to get that specific path. Now, adjacencies are formed only between designated routers and backup designated routers, and these backup designated routers and the normal routers, the normal OSPF routers, occupy different multicasts. We talked about neighbors or OSP, which are basically OSPF neighbors or routers joining the multicast address of 224.0.0.5 in IP version 4 and FF02:5 in IP version 6. Those are all OSPF routers. But when you're talking about designated routers, they join the group, the multicast address of 224.0.0.6, and in IP version 6, that is FF02:6. These are all designated routers. Now, talking about designated routers, what is a designated router? A designated router is a router that is assigned the role of receiving the LSUs and the database description packets. LSUs for link state update packets and the database description packets. So a designated router will pass information on behalf of the others. We were talking about an estate, and we said that we have what we call as neighbors. But if all of us as neighbors were talking to each other, then there would be a lot of confusion in that communication flow. So we need one neighbor to be assigned that specific role of giving us information. So you choose one router to give information to the next or to the other routers in that specific network. Now, the way we calculate the number of adjacencies in a network is the n multiplied by n minus 1, and all of that you divide by 2, where n is the number of routers. And we have said the designated router is that router that has taken the responsibility of receiving the link state updates and the database description packets for that specific OSPF area. Now, if a designated router fails, we also configure what is called as a backup designated router, and that is supposed to offer failover services in case of failure of a router. Now, in case of large deployments, you could deploy different OSPF areas. That is, you use Dextra algorithm to work on different OSPF areas to reduce the resources required to run the algorithm on a large network. And you don't basically have to break your areas, since OSPF can support a couple of hundred of routers. So if your application of your application of OSPF is in the range of 100. So if OSPF is supposed to run on a couple of hundred of routers in your network, then you don't have to break the OSPF area into different OSPF areas. But if you do so, what enables us to communicate between the two OSPF areas is what we call as an area border router, and this sits at the border of at least 2 areas, so that it's able to communicate with the 2 OSPF areas. By default, area 0 is the backbone area, and can be denoted by the 4 decimal notation of 0.0.0.0 or 0 as a decimal. Now, how do we calculate the path cost of an OSPF router or an OSPF router interface? And we do this by taking the reference bandwidth, which is by default 100, and dividing it by the actual interface bandwidth. So for example, you have an interface bandwidth of 100 Mbps and the reference bandwidth is 100 Mbps. So you're going to divide 100 by 100, and you're going to get the cost of that path being 1. If you have an interface bandwidth of 1 gigabyte, that is 1000 MB, then you're going to take 100 MB, divide by 1000, and you're going to get the OSPF path cost of that being 0.1. So that is how OSPF works. Let us now look at an external gateway protocol, which is BGP, and this helps us to communicate from one autonomous system to another autonomous system. Remember, we talked about autonomous system being a system being in one administrative control. Okay, so BGP helps us to communicate between two networks with the two different administrative controls. It's an exterior gateway protocol, and BGP is of two types. You have interior BGP and exterior BGP, and BGP works by forming neighborships, and this neighbor's IP address is explicitly configured. You have to configure that neighbor's IP address, and the neighbors advertise layer leachability information, that is network layer leachability information, and advertises a collection of path attributes that is used for path selection. We talked about the list of paths and other attributes that could be used in the path selection. It is a path vector routing protocol, meaning that it considers path attributes in order to decide on which route to use to route its packets. So that's it when it comes to this video on routing protocols. I promised to give videos on ERGIP and ISIS later, so kindly stick for that. Stay tuned for that, and I hope to see you in those videos. So thank you for joining me, and see you in the next video. Peace, guys.